Hi, my name is Philip. Today I will present our paper LCIM, Mining Low-Cost High-Utility Item Set. This paper, if you want to find the code and the dataset, also you can find in the SPMF software. Okay, so let me give you some introduction. Nowadays we have a lot of data in databases. We can use the machine learning, the artificial intelligence to do a lot of things like predictions. But also we have a need to be able to understand the data. So not just build some models that are the black boxes, but also to have a way to find interesting information in the data. So there's a field in data mining called pattern mining, where we use algorithm to search for patterns in the data that looks interesting and will give us some insights about the data. These patterns we want to find in the data, they can also be interpretable. That means easy to understand by the humans. There have been a lot of work in data mining about frequent item set mining. That means to find patterns that appear many times in the data. For example, if you want to analyze the shopping data, you could find what the people like to buy many times together. But this is not everything. There are also other types of patterns that people want to find in data. Recently, there have been a lot of work on high-utility item set mining. High-utility, it means the patterns that have the high importance. For example, for shopping, high utility means we want to find the items the people buy together that make a lot of money. And this can be more interesting for the user than finding what the people buy often. Okay, we want to find what has the high importance, like the money, for example. So let me show you briefly the problem of high-utility item set mining. Then I will talk to you about the new problem in this paper. So in a high-utility item set mining, we have as input a database, as you can see on top. And this database here has many transactions, like for shopping, okay, T1 to T7. In T1, we have, for example, the customer buy A and C, like apple and cake. And we have the numbers, like A1 means one apple, one cake. And then also we have another table that tells us about the money for each item, like A for apple is a $5 profit, B for bread is a $2, and so on. And the goal in such the database like this, we call a transaction database, we set a parameter, the minimum utility, like a minimum amount of money, like $30, and we want to find all the high utility item set. That means the sets of products that people buy together that make a lot of money, at least the minimum of like $30 in my example. So here you see the output. We find different sets of items the people buy and make a lot of money, like BE, like bread and eggs, make 31. It is more than 30, so we say it is high utility item set. So there have been a lot of algorithms for this problem about finding the high utility item set in the data. But there are some limitations I want to highlight today. First, in high utility item set mining, we focus on the utility of patterns. We want to find patterns that have the high utility. Utility means, for example, the benefit like the money. However, this problem will ignore the cost or the effort to obtain these benefits. So we only look at utility, but we don't think about the cost. So because of this, we might find many patterns that have the high utility but also a very high cost, or that have a low cost but a relatively high utility. We might miss them, for example. So what I want to say here is that utility is not everything. Sometimes there's another dimension we call the cost that is also important. I will show you some examples. So in this paper, what we want to do, we propose a new problem called the low-cost, high-utility item set mining. The goal is we want to find sets of values, some item set in the data, that have the high utility but the low cost. So high utility means the high benefits, but the low cost in terms of cost means, for example, the money, the time, or the resources that we use. Okay. So let me give you two examples why we want to do this. For example, in e-learning, okay, we could have some database of transactions about the activities that some students take in some online environment. Then the cost will be the time that the student takes for each activity, and the utility could be the grades that they obtain at the final exam. So then we could find the low-cost, high-utility item set. That means the activity that don't requires a lot of effort, but will help the students to get the very high grades, for example, so to study more efficiently. Another example is for the medical data. We could have some transactions. We have the list of treatments by different patients in a hospital. The cost will be the time or money that you spend for these treatments, and the utility will be the result, like you are cured or not. So then we could find the item set, the sets of treatments that have a small cost and will help the people to get cured. Okay. So those are two motivation examples that are the motivation for this work. So now we have two dimensions, utility and cost. So how can we combine them in the same problem? So there's a simple solution. It will be to subtract the cost from the utility. So we take the utility and we remove the cost from this, and then we use the high utility item set mining algorithm. So that will be easy. But there's a problem. The utility and cost, often they might be expressed using different units. Like the utility could be the money, and the cost could be the hours or other things. So maybe it does not make sense to subtract the cost from the utility. So after thinking about this, in this paper, we decide to model the cost and utility separately. So because of this, we can use different units for the cost and utility, like the hours, the grade, the money, and so on. And also, it will allow us to calculate the average utility and average cost, which we think are more meaningful for the user. So for example, it is more interesting to know that students usually they take an average time of 30 minutes. This is the average cost, okay? But this is more interesting than knowing that the students totally they took 1,000 minutes. But this is not very useful. But on average, the student take 30 minutes. So this is more interesting. So we believe that by modeling utility and cost separately, we can have the average utility, average cost, and this may be more interesting. Okay, so there have been a lot of paper on pattern mining to find the frequent item set, the high utility item sets also. But all these algorithms, they don't have the concept of cost. So how to add the cost in this? For the sequential patterns, to find the patterns in the sequences, we did a work before where we used the cost and the utility. But still, analyzing the sequences is different from analyzing the transactions to find the item sets. So we cannot just reuse the same algorithm. So in this paper, we designed some new algorithms. So first, let me give you a more formal problem definition to explain what we want to do. So here as input, I have a transaction database with the utility and also the cost values. It is different than the database in high utility item set mining, as I will explain. So how does it work? Let's say that we have a set of items we call I. So here in my example, it will be some learning activity we call A, B, C, D, E, F, G. And then we say an item set is a set of items like A, B together. Okay, it is, for example, a set of activities that a student could take. Now, we say that a database, as you see on top, is a set of transactions we call T. Okay, T1, T2, T3, T4, T5. So here we have 4 transactions. For example, 5 transactions, for example, from 5 students. Now, each transaction will be a set of items. So here, for example, the transaction 5, it means that a student took the learning activity B, C, E, and G. Okay. So this data could be also something else, not just about e-learning, but here I use the example of e-learning to illustrate the problem. Now also in each transaction, each item like B will have also a cost value. So here we have B4. It means the student 5 took 4 minutes to do the activity B and 2 minutes to do activity C and so on. Okay. Also in each transaction we have a utility value that indicates some benefits. So for example, the student 5 did many activities and this is the benefit. You got 21 points at the final exam. Okay, so we have also utility. So here, one thing I want to say, the utility is not exactly like in high utility item set mining. Here the utility is for the whole transaction, it's not for each item. Now, what we want to do in this problem, we have the input on top. We have 3 parameters we call the minimum support, minimum utility, and maximum cost. Our goal will be to find all the low-cost, high-utility item sets. We say an item set X is a low-cost, high-utility item set if its average utility will be more than the parameter, the minimum utility. Its average cost will be less or equal to the maximum cost, the parameter, and its support will be at least the minimum support, another parameter. So now let me show you how to calculate these values. We'll take an example. Let's look at the item set BC. BC appear together in transaction 1, 2, and 5, transaction 5. Now, if we want to calculate the values, like the support means how many transactions contain BC. So here we have T1, T2, T5. So we say the support of BC is a 3. Now for the average utility, we take the utility for all the transactions with BC, 40, 20, and 21. There are 3 of them, so on average, when we do this activity, the utility on average will be 27, like the average grade, for example, for e-learning. And the average cost will be all the costs for BC, like 10, 1, 8, 3, 4, and 2. We do the sum divided by the number of transactions. So that means on average, the people do the activities BC, they spend 9.3 minutes and get an average grade of 27. So based on the parameter we select in this problem, we can find all the low-cost, high-utility item set that have the average utility more than minimum utility, the cost less than or equal to max cost and the support more than the minimum support. So now how to solve that problem? We design an algorithm called LCIM to find the solution quickly for this problem. It is an algorithm that will start from item sets that contain the single item and then combine them to make the larger item set. So first we have, for example, 2 items. We combine together. We get an item set with 2 items, and then we combine together to get 3 items, and so on. It will use a depth first search, a little bit like you can see here. So first we find the single item like A, B, C, D. Then we combine A with B to get AB, A with C to get AC, and so on. Okay. And then we will explore the different possibilities, but to avoid looking at all the possibilities, we will use also some search space pruning property to help us avoid looking at all the combinations. This is important if we want to design an efficient algorithm. So how to avoid exploring the search space, the whole search space? There are some properties. One of them, very famous, is called the support pruning. If you have 2 item set X that is a subset of Y, you know that the support of X will be more than the support of Y. So that means if you have an item set like AB, the superset like ABC can only have the support that will be equal or less. So with this we can avoid many combinations. Okay. So I don't want to go too much in detail, so we'll continue. Another pruning property is about the cost. This is something new in this paper. We use some lower bound on the cost. And using this lower bound, we call ACB, we find that if the ACB of X is more than the max cost, we don't need to look at all the supersets of X. So we can save a lot of time. Okay. So again, here, this lower bound is a little bit complicated, so I will not explain the details in this presentation. But if you are interested, you can look in the paper to see all the explanation with some examples. Now also in this algorithm, we will use some special data structure we call the cost list data structure. So the idea, I will just explain the main idea. We have some item set like A, B, or AB. So for each item set that the algorithm will consider in the search space, we build a table like this. Okay. The table, like the table for A, the cost list of A, will tell us about its utility, cost, the transaction that contain A, and the cost value of A in these transactions. We have the same for B, and then we can combine this table to find the table of AB and so on. So the algorithm will use this to quickly find the cost and utility of the different item set when searching. So here again, I will not explain all the details. This is more about the algorithm itself. You can look up in the paper for more details. So here we have the algorithm. Okay, I will skip the details. And also in the algorithm, we have 2 optimization we use to also improve the performance. Okay, so using some matrix and also some other method to speed up the construction of the table, the cost list. So we did some experiment to evaluate our algorithm. We use 4 databases used in pattern mining, and one of them is a special database called e-learning about the learning. Okay, and it has the real cost and utility value. So this is very interesting to test our algorithm to show it is useful in real life. So we compare 2 versions, LCIM and a baseline that is LCIM without the optimization. So we did different experiments on the 4 data sets. So we changed the parameter, the minimum support, and also the max cost and minimum utility. And we look at the number of patterns, but also at the time. And we see, for example, when we decrease the minimum support, the time will increase, and also the number of patterns. This is really reasonable. It is what we find also in other papers in pattern mining. And some other observation about the cost and utility, we find the utility does not change a lot because we don't use it for pruning. So it has not much influence on the time and so on. But for the cost, it can have some influence in general. Okay. So we have the results for all the database, and also in some database we see the baseline is faster than the LCIM, or LCIM sometimes is faster than the baseline. So it really depends on the database. The optimization can help or not. So in conclusion, the observation about this, LCIM is not always faster than the baseline. When we increase the max cost, the time will increase because there will be more patterns, and the same for minimum support. And the minimum utility does not have a big influence on the performance because we don't use for pruning. We also look at the real e-learning data to find the real patterns. So in the e-learning database, we have the data from 54 students about the activities they did in the e-learning environment, and it has the real cost and utility values. So we set the parameter, the minimum utility, max cost, and minimum support to try to find some interesting patterns. So here I show you some patterns we find in the database. So here you see some activities, and also we have the average utility to do these activities, the average cost, and the support. And also we calculate something interesting we call the trade-off. It is the ratio of the cost to the utility. So using the trade-off, you can compare the cost to the utility to see which pattern is more efficient actually. Okay, so the patterns that will have the high or the low trade-off can help us to select the best pattern, maybe for studying in the e-learning environment. So this is the main idea about this. So in general, we want to find the patterns that have the high utility but the low cost. So for example, this pattern 0.8 has a higher utility than the cost, so it will be better. The trade-off is smaller. But the other pattern here 7 has a utility, the cost is much higher than the utility on average, so the trade-off is really high. Okay, so it's not a very good pattern. I mean, if we only look at these measures, okay, we can also look into more details about the real application also. Okay, we should. So in conclusion, we define a new problem called the low-cost high-utility item set mining. We define a new algorithm, and the big innovation in this work is to combine the cost and utility in item set mining. Nobody has done this before, according to what we know. And we define some search-based pruning property and some optimizations. And there are many opportunities for future work. We could design the better algorithm, add some more optimization, extend the problem for top key, close item set mining, maximal item set, and so on. If you want the code and also the database for this algorithm, you can find them on the SPMF website. It is in Java and open source. You can also use this in your research. So that's all for this presentation. Thank you for watching.